Good evening, and welcome to the Unitarian Universalist Congregation of York. And we welcome you to York's Earth Month speaker series. I'm Jim Smoker. I serve as co-facilitator of the UUCY Green Action Team. And we invite you to participate in our speaker series this month, each Thursday at 7 o'clock. Prior to Earth Day and Earth Day Sunday. We also invite UUCY members, friends, and youth to participate in our environmental justice workshop, which will be held on April 30th from about 9 a.m. until dusk. No, until about maybe noon at the very latest, at which time we hope to engage the congregation in mapping out the future direction of our environmental and justice work as a congregation. Paul Duryea, Deb Gonyak, Steve Snell, Mike Robinson, and I serve as kind of the core group at this point of the Green Action Team. At this time, it's my pleasure to introduce our first speaker for the month, Dr. Keith Peterman. Dr. Peterman was a former friend of the UUCY for a number of years, and is a distinguished professor emeritus of chemistry at York College of Pennsylvania. He has served as a Fulbright Scholar, a National Academy of Sciences Research Scholar, and author of and co-author of 5 recent textbooks on books on climate change. We'd like you to have your cell phones on mute, and for those in the Zoom audience, if you haven't been muted by our host, we ask you to mute at this time. Thank you, Dr. Peterman.
All right. Well, I guess I'd like to start off by saying thank you to everybody for inviting me to speak to you. I guess we're all in the same boat. We're just trying to save the world. It's nice to be back at UU. I very much enjoyed the time that I did spend here and the spiritual enrichment that I got. I especially enjoyed the men's group, and I see some of them here tonight. So I thank you for inviting me back. So with that, I guess we start the presentation all right, if we're looking here. Next slide. So basically what we're going to do tonight, the title of the journey is Climate Change, a Global Journey. And our planet faces a climate emergency. And if we're going to find a solution to our planetary fever, what we must be able to do is we must be able to clearly articulate and understand the problem. So what I'm going to try to do for the first 2/3 of my presentation is to try to understand the problem, and then the latter third, propose some solutions. So next slide. For the purpose of our journey tonight, we're going to start in Costa Rica, a tiny little nation in Central America there, sandwiched between Nicaragua and Panama. Right. And we're going to begin our journey in the cloud forest of Monteverde Cloud Forest, eventually head out around the globe. Looking there to the right, we're going to visit various locations around the globe. Toward the end of the talk, we'll return to Costa Rica once again to a dry coastal forest area where we're going to talk about ecosystem services. So let the journey begin. A little bit of a comment about the cloud forest itself, basically how it's formed, or why the cloud forest is such a rich area on the planet. It's one of the most biologically diverse areas on the planet. The warm ocean, or the warm winds sweep across the Atlantic Ocean, across the Caribbean. They strike, in the case of Costa Rica here, the Tiburon Mountains. They sweep upward. The air expands, it cools, and when it does that, it drops rain. Therefore, the eastern flank of the mountain is a rainforest area, continues on up. We have a cloud deck that enshrouds the top of the mountain many days out of the year, and then it dissipates, and on the western coast, we find it's a dry coastal area. So this next picture is just one I took that sort of reflects what the cloud forest, the cloud may look like settling down over the top of the mountain. Next one. And the reason we're here is to talk a little bit about the golden toad. It was discovered in 1964 by a young Quaker by the name of Jerry James. It was subsequently published in the literature, so there is scientific documentation for the golden toad in 1966 by J. Savage. This is, it's endemic to the cloud forest, which means its residence is on the mountaintop. And on this right-hand slide, we see some of my former students who are walking down right on the Continental Divide. It's one of my favorite little treks in the world, going down that Continental Divide. The golden toad's habitat was about 8 kilometers long on that Continental Divide and about 1.5 kilometers over the top of the mountain. Next slide. As the naturalists tell it, when the spring rains would come in late April, early May, the golden toads would emerge. They would not be seen any time else in the year except for about a 10-day to 2-day period. Males would come out first. There'd be about 8 males to every female. Of course, the males don't look like a toad, being golden. That's what made them so unique. You see on the right-hand side, a male latches onto the female, as would happen. It would be quite a competition when it's an 8-to-1 ratio. Other males may try to latch on top. They're sexually dimorphic. The female is much larger and looks more like a toad than the male. They may end up competing so much that the males get so deep that they would even drown the female beneath. And there are more stories to go with this. If we take a look at the next slide, they were, one of the researchers was getting set up to do some studies in 1988, and they had set up their field study. A Quaker by the name of Wolf Gwyndon, a well-known naturalist, was to go out and let them know when the golden toads emerged. He tramped all over the mountaintop in late April, early May, could only find a single golden toad. So there was no research took place. The following year, the same thing happened. He went up, trampled all over the mountaintop, looked around, saw but a single toad. Some think it may be the same toad that was there the previous year waiting for a mate. It has not been seen since. It was declared extinct due to climate change. Dr. Alan Pound, shown in this slide here, is the lead researcher who published the seminal article in 1999 that declared the golden toad extinct due to climate change. This represents the first species-level extinction linked to climate change. The situation gets even more grave. Dr. Pounds and a dozen other researchers from Central and South America compiled all the data on the harlequin frogs and discovered that 110 species of the brightly colored harlequin frogs had disappeared over a 2-decade period. They compiled the data and published the article, and in 2006, this becomes a seminal article which declares the first mass species level extinction linked to climate change. So here we are on this slide. Dr. Pounds has spoken to my students over a 2-decade period, and he and other scientists have collected now decades of instrumental data, and he presented the copious numbers of graphs and so forth. And in summary, what he's found is for Monteverde, it's getting hotter and colder and wetter and drier. And he takes it, meaning that there are more hot days stuck together, more cold days stuck together. You get deluges instead of canopy drip. You get actually very, very many dry days stuck together, which is not good for species. He takes these graphs and overlays them when we see the same thing is happening in other parts of the world, globally. It's not just the golden toad, however, not just species extinction. For birders here, and I know a couple of you have just returned from Costa Rica, and I did, and was on the same flight going there, just by chance. One of the birds all would like to see would be the resplendent quetzal shown here. It nests on the mountaintop of the cloud forest. Next slide. It is at risk because as the conditions are changing in the cloud forest and the cloud forest canopy is lifting, low elevation species are beginning to move upslope. Among these is the keel-billed toucan. The keel-billed toucan, it's not just species redistribution, but now it's a matter of species encroachment because it now is competing with the quetzal for nesting spots. It's competing for its protein sources of food. And it's also been observed to be eating the quetzal eggs, which now puts the resplendent quetzal at risk. So before I go further, I want to address a question I'm asking almost every time I give a presentation, and it is, with all the climate alarmism, doesn't our climate just vary naturally anyway? The answer is that is unequivocally yes. One of the major contributors to climate variability is volcanoes. So if we board a flight and head to the other side of the Pacific, 75% of all the volcanoes, active volcanoes in the world, are in the Pacific Ring. Next slide. We can go over to Mount Pinatubo, which represents the largest volcanic eruption in the 20th century, 1991. When that volcano erupted, it spewed lots of gases into the atmosphere and cooled the planet for a period of nearly 2 years by about 2 degrees C. Basically, the way this happens is when volcanoes erupt, they don't just blast boulders and stones and ash, but they also blast gases into the upper atmosphere. Here, if you look on the left-hand side of the slide going up to the stratosphere, we have sulfur dioxide. That goes through a series of chemical processes, ending up as sulfate aerosols. Those sulfate aerosols reflect incoming light, which is what caused the planet to cool, much like if you're laying on a beach enjoying the sun, a cloud comes over, you feel cool immediately, except this becomes a global phenomena. Next. However, volcanic eruptions are episodic and they are transient. They cause negative radiative forcing, which means they do cause cooling, but that it is temporary. Typically, the aerosols will settle out in 12 to 14 months. As I said, Mount Pinatubo being so large, it actually lasts for about a 2-year period. Another major contributor to climate variability is solar variation. These are called Milankovitch cycles. The Earth travels around the sun in an ellipse, but that ellipse does not remain constant. Rather, there is an eccentricity, meaning it changes the shape of the ellipse over time. As well as the Earth tilts, and that tilt will change over time, and it wobbles or precesses like a top. Next slide. These Milankovitch cycles have been found, the orbit, tilt, and wobble have been found to converge in cycles over time. These cycles are what have been found to drive the ice ages. Based upon the Milankovitch cycles, however, we will not enter an ice age for another 30,000 years. The conclusion is natural cooling will not offset current warming. Next. This is a slide I grabbed out of the most recent Intergovernmental Panel on Climate Change, the Physical Science Basis Working Group 1, released at the end of 2021. What you can see from it is the black line. Basically, if you look at zero is a baseline temperature. Anything on the left-hand side of this graph going negative would be below this zero temperature. We call it a temperature anomaly. Anything above it would be a positive temperature anomaly from the base. Beginning about the onset of the Industrial Revolution, we can see that the temperature was relatively constant, but by about mid-20th century, we started to see a significant temperature increase. That is what's actually occurring, the black line. If you look at the blue line on the bottom, the bright blue line is the average of many modeling groups and simulations and so forth. It's the average of those, and that incorporates all natural radiative forcing. Volcanoes, solar variation, but all sorts of other natural forcings are included there. What you can see from this is that natural variability will not explain late 20th century warming. However, looking at the brown line that's going up, the solid brown line is the average of many, many models, modeling groups, and simulations from around the planet. That brown line, very close, when you throw in human contributions, you see that the brown line comes very close to approximating what we're actually observing the black line. The summary statement is very clear. Humans are responsible for late 20th century warming and beyond. So why is our climate changing? Next slide. The sun warms the planet. The sun's light, however, is not heat. The sun's light is light. It comes across that void of that vacuum of outer space. When it strikes our atmosphere, some of it may be reflected by clouds. Some may come through, be reflected by the Earth's surface. Snow reflects much better than will a dark plowed field. Some of the light, however, is absorbed. When that light is absorbed, it undergoes transitions and can end up as heat energy. A hot object gives off infrared radiation. We are all hot objects in here. How's that? We are all giving off infrared radiation at this point. That infrared radiation that's given off by our warm planet can go back into the atmosphere, be absorbed by carbon dioxide in the atmosphere, which is only a trace gas, about 0.04%, but it's a very important trace gas because when it absorbs the infrared radiation, it will now re-radiate that light out into the universe, but some of it will be radiated back toward the planet. That re-radiation back toward the planet is what keeps our planet warm, and if it was not for that effect, which we now call the greenhouse effect, this would be a cold, lifeless planet on which we live. Next slide. So is the greenhouse effect good or bad? Well, the greenhouse effect is good. It is the enhanced greenhouse effect that is bad. The enhanced greenhouse effect is due to increasing concentrations of carbon dioxide in the atmosphere. This brings us to the Keeling Curve. Dave Keeling was a graduate, or was a postdoc at the time. He set up instrumentation on top of Mauna Loa Peak in Hawaii. In 1958, he recorded the first truly instrumentally active measurement for carbon dioxide in the atmosphere at 313 parts per million. That's a very important number, 313 parts per million. He also made two very important discoveries after a period of about 3 years. He published an article, and in this article, he made two very clear observations. Number one, our planet is breathing, and number two, the concentration of CO2 in the atmosphere is increasing. On the next one, we'll look at how our planet is breathing. I took a snippet of the data that's plotted right here, and I deliberately picked one just before we passed over the 400 ppm threshold back in 2014. But if you focus your attention to the bottom of the plot, look at October 2011. The data point there, 388.96 ppm. Also, look, these are high accuracy, high precision numbers. So start in October. If you count those red data points, October, November, December, January, February, March, April, May, you see in May it peaks out at 396 parts per million, May 2012. You then can follow data points, May go to June, July, August, September, October, bottoms out once again. The cycle repeats itself. Well, why does it drop going from May down to May 2012? Why is it dropping? All we have to do is look out the window now. It's April. What do we observe? We see the dormancy of the plants is beginning to end. We're starting to see leaves. We see vegetation growing. This is Northern Hemisphere data. Photosynthesis, we're sequestering carbon dioxide from the atmosphere. We see that the CO2 concentration drops. You hit October, November, dormancy sets in. When it does, during the winter months, transpiration takes place, CO2 ends up going back into the atmosphere. You also can see what the slope of the line looks like. So on the next slide, we'll look at the full Keeling Curve to date, and this is the latest data that's up that I even looked this morning, so the March data is not up yet for last month, but basically it's almost 420 parts per million. The red line is that seesaw seasonal line that we're looking at. What you can see is that since 1958, when I was a 10-year-old boy, just in my lifetime, the CO2 concentration has increased well over 100 parts per million. So currently it's 420 parts per million. So our planet's breathing, the CO2 concentration is increasing. It's not even linear. You can see it is sort of accelerating upward. Parallel to that, if you look at what has happened to the temperature, once again, you take a look at the 0 point on the graph. The zero plot going across is going to be our reference point. Anything that's negative would be the temperature anomaly below that reference point. Anything that's positive would be the temperature above that zero reference. Beginning about the onset of the Industrial Revolution, you can see our temperature remains relatively constant, even going through early 20th century. Once we got the latter part of the 20th century and beyond, we see that the temperature of the planet begins to increase quite dramatically. 19 of the 20th years on record have all occurred just in this century that we're in right now. Let's talk about the other CO2 problem, ocean acidification. And I apologize for some of these graphs, but I think these are the most important graphs for us to truly understand the nature of the problem that we're dealing with. So ocean acidification. Once again, if you look at the red seesaw oscillating line that's going up, that is the Keeling Curve. That's from Mauna Loa Peak. And if you see the map there on the right-hand side, Station Mauna Loa. If you go to the upper left, you'll see Station Aloha. This is recording seawater data right near Mauna Loa Peak. As the Keeling Curve is increasing, the CO2 atmospheric pressure is increasing, what we find is that the CO2 that's dissolved in the ocean is increasing right along with it. Much like when you have a carbonated beverage, the higher the concentration of CO2 on the surface of that beverage, the more carbonated it becomes. The same thing is happening here. Carbon dioxide serves as an acid when dissolved in water. Well, something is acidic. We've learned in elementary school, low pH is acidic. So as the concentration of CO2 is increasing, it's becoming more acidic. The ocean is becoming more, the pH of the ocean is beginning to drop. Along with the drop in pH, we now have the issues that are being confronted with things like coral reefs, mollusks, the dissolving of shells, and other adverse effects within the ecological system. We'll get away from the graphs for a second. I hope that you got a good picture from the data. That's the scientific data. Let's look at nature's most visible indicator of climate change, which are glaciers. I'll go here. I'm sure that many of you in here have visited Glacier National Park. They have a repeat photography project. I just picked two images right here, one that are for Grinnell Glacier. It was stated in Glacier National Park that all glaciers would disappear by 2021. That was some earlier studies. They did not disappear. The park removed those signs. However, they have dramatically diminished in number and in mass. You can see here, Grinnell Glacier is one example. On the left-hand side is what it looked like in 1938. On the right-hand side is what it looked like in 2019. Go to the next one. I spent some time on the Rhone Glacier in Switzerland. This is a picture I took staying at the Belvedere Hotel as a lone individual when they had just opened the season. But looking across there, if you look at the Grinnell Glacier back in 1930, you can see where the glacier was. Here you can see the top of the glacial moraine on the right-hand side of the picture. The glacier tongue has receded way up the valley. Next one. If we go down into the valley and look backward once again, there's an etching from 1859 for the tongue of the glacier. I tried to get a picture from the same vantage point. That's not the glacier that you're seeing there. That's the rock face on the right-hand side. You have to go up over the top, go back up, and the glacier is receding. Glaciers are receding around the planet, land-based glaciers. Next. The second largest glacier on the planet is Greenland. The meltwater in Greenland is the single largest contributor currently to sea level rise. The mass loss that's being observed exceeds any that we've observed in the past 12,000 years. And studies and models suggest that it may have itself exceeded or have melted beyond the point of no return. Back to the graphs again. If you look at sea level is rising, we know that, and island nations are at risk, low-lying areas and so forth at risk. If you go back to 2005 on these graphs, look at the red graph, which is thermal expansion, and the blue graph, which has to do with meltwater that's entering the ocean. In 2005, they about equally contributed. Now, thermal expansion, first of all, as water warms, it expands. Our warming ocean is expanding, and that's contributing to sea level rise. Also, land-based glaciers, as they're melting, they are dumping water into the ocean. That also is making the ocean rise. That happened to be about equal contributions. The ocean was rising, but they were about equally contributing back in 2005. If we advance now to today, what you can see is clearly the melting of land-based glaciers and ice is significantly contributing more water than is thermal expansion. Those two lines added together, the net is the top line. It's more or less of a sort of a purple shade color there, right there. Next. So sea level rise is of great concern. We're looking at how rapidly Greenland is melting. Also of concern is the slowing down and possibly even stopping of the thermal hairline circulation, which is the ocean conveyor belt. Time doesn't permit me to go through the details of how this or why this occurs, but what we can say is that this ocean conveyor belt carries warmer temperatures from the tropical areas up through the North Atlantic That's what warms Europe, gives us a Gulf Stream that warms us here in the North America as well. As Greenland melts, it dumps fresh water into the North Atlantic, and that's really the engine that's driving the ocean conveyor. If that engine slows down due to fresh water dumping in and slows down the ocean conveyor, we have a high latitude nations like Europe who are going to be at great risk because they will no longer have the moderated temperatures they have right now. Next. So basically what we could say is our planet is experiencing climate disruption. As we saw in Monteverdi, around the planet, you could look at lots and lots and lots of data. It's getting hotter and colder and wetter and drier. I think this is quite clear. I think we see it in the news. You see greater deluges, much more powerful storms. There's reasons for that because of the energy that's stored in gaseous water. We see droughts, longer droughts, more wildfires. All of this is quite well documented. Now would be an appropriate time for us to talk about, with getting some of the scientific background, climate justice and climate and health. However, those are the topics of your next two speakers. So I'm going to skip right over those and jump into policy. I'd like you to answer the question, think in your own mind, which U.S. president said this? If we've learned any lessons during the past few decades, perhaps the most important is that preservation of our environment is not a partisan challenge. It's common sense. Our physical health, our social happiness, and our economic well-being will be sustained only by all of us working in partnership as thoughtful, effective stewards of our natural resources. Possibly a good choice. What is it? Richard Nixon. Let's look. Jimmy Carter. Ronald Reagan. A Republican president said that in 1984. I will commend President Reagan on another matter, and he led the very first global environmental treaty ever, was the Montreal Protocol, which we signed on to in 1987, went into force in 1989, and it had to do, there's a whole story behind that, but it had to do with CFCs, chlorofluorocarbons, and the ozone layer. Actually, that problem has been largely solved, not completely. There's still some cheating and other things going on, but the ozone layer is recovering. First truly global treaty, and we credit him for that. Next slide. Then we come to George H.W. Bush. George H.W. Bush, when he was stumping for the presidency, said, "Those of you who think we can't solve the greenhouse effect do not understand the power of the White House effect." He also was a global leader, went to Rio in 1992, and he signed the United States onto the United Nations Framework Convention on Climate Change, a Republican president. I think that's very important to understand the history of this. Next. The United Nations Framework Convention on Climate Change. What is it? First of all, the word convention here does not mean you're going to a hotel and you're going in for meetings. Convention in this context means treaty. So reframing that, it's the UN Framework Treaty on Climate Change. The purpose of that treaty is, the ultimate aim is to prevent dangerous human interference in the climate system. Now, it provides only a framework to fill in all the missing pieces, and all the sub-treaties and so forth that need to happen. There is an annual conference of parties, or what is otherwise is known as a COP, which meets annually. I had the good fortune, attending my first COP in 2009. And I carry press credentials, so I'm a UN accredited member of the press, as is my colleague right here in the front row, Greg Foy. Thank you, York Daily Record. We're grandfathered. We're in there. We get to go every year. So it's great. This is an exciting time for me because I thought I was going to witness what world leaders were going to witness. Here's President Obama going through the press room. Not a very good picture because I grabbed my camera, didn't have it focused, but I had to put it in there anyway. Next slide. Copenhagen had been termed Hopenhagen in 2009. After moving in on 20 years of inaction, finally we were going to have action on climate change. We saw the largest gathering of world leaders ever outside the UN in New York. 100,000 people converged on Copenhagen. And they went with the idea they're going to put their signature on a historic document. In the end, due to wrangling over self-interest, finances, historical responsibility, the same thing year after year. The best they could do was take note. The world leaders were left back. We take note of the Copenhagen Accord, kick the can down the road one more time. Next one. I'm now going to jump to 2015 without going through all the COPs. 2015, we once again, all right, flip that. In 2015, we're going to go to Paris. We once again saw a huge gathering of world leaders who arrived in Paris. This time, however, they arrived for the opening session of the COP. They all gave their grand speeches. If you read them, they're all saying the same thing. World leaders around the globe, they're all saying, this needs to be solved. This needs to be done. We all get it. The science is clear. Everybody says the same thing. This is an iconic photo you're seeing here on the right-hand side. This is the largest gathering of world leaders collectively to ever gather for a single photo that we see right there. Next. In Paris, they got the job done. Finally, notice what this is. This is COP21. After 20 previous COPs in COP21, it now has universal membership. All nations have signed on to the United Nations Framework Convention of Climate Change. They have all agreed to the Paris Agreement. Next slide. Why did they do that? Well, we had something known as nastily determined contributions. These are voluntary contributions. It's quite clear that based upon the climate denial that is currently present in the U.S. Senate, that there is no way that we could get a climate treaty adopted or ratified through the Senate. However, we can use
existing legal authority through the Clean Air Act and other acts to be able to make contributions. So nations are making contributions based upon their political realities within their own countries. These are voluntary. The Paris Agreement says that we're going to make every effort to keep the temperature increase of the planet below 2 degrees C with efforts to limit it to 1.5 degrees C. Why 1.5? That's where island nations disappear. They're required to communicate ambitious efforts over time, and they should make progression over time. Next one. This is the current nationally determined the NDC for the United States where we stand, and if you look, you go to the black line, or our emissions, look at the green line at the end of that, you can see that by 2025, or sorry, what we're going to look at I can't even see my own slides right there. By 2030, by 2030, we're to lower greenhouse emissions by 50 to 52%, and we're to be net zero by the time we get to mid-century. Next one. This slide I grabbed from the IPCC, the Intergovernmental Panel on Climate Change Working Group 2 report that was just released in February. If you look at the graph, left-hand side is the temperature, and we can see the temperature going up. That's our planetary fever, 0.5, 1.5 on the left-hand axis. If you look on the x-axis on the bottom, we can see gigatons of CO2. What is quite clear is we see the amount of CO2 we're putting into the atmosphere, it directly mirrors the warming of the planet. It's a near linear relationship. Next one. Now I want to look at a paleoclimate. Going back 800,000 years. On the left-hand side, you see a scale for temperature. On the right-hand side, you see a scale for carbon dioxide concentrations in parts per million. The dark blue line is carbon dioxide concentration. The light blue line is temperature of the planet. We can see that there's a correlation between the two. What you will observe is during the last 800,000 years, the CO2 concentration of the planet has never exceeded 300 parts per million. Going back through paleoclimate, and you could go back further, but we can see it has never exceeded 300 parts per million. Next one. Oh, I'm sorry. Go back to this. I want to point one other thing. That red line, I put that red line in the graph, that represents the Anthropocene, which is the Keeling Curve during the Anthropocene. So we'll go to the next. It brings us to the Anthropocene, or the age of humans. Next. This is otherwise known as the Great Acceleration. We are currently in the Anthropocene. I may have been born in the Holocene, but it's still, we'll know that. It's in 2022, we're going to get a better picture. So we're making that for formality. But in terms of the sciences have accepted we are now in the Anthropocene. Next. The Great Acceleration began to occur in mid-20th century, and it was a great acceleration of both material and energy consumption, along with this massive amounts of waste. There have been large-scale chemical perturbations around the planet. Plastic waste is enormous. Estimates are, models show that the mass of plastic in the ocean may be greater than that of sea life by mid-20th century. There's been changes to the global climate we've talked about, sea level rise, ocean acidification, unprecedented levels of species redistribution. Species are undergoing redistribution on every continent and in every ocean. It's very clear that humans are leaving a trace, a clear trace on our stratigraphic record. Next. This is a graph I created just to give some visual clarity to some numbers that came out of a report that the Intergovernmental Panel on Climate Change was asked to create in response to the Paris Agreement. You know, what is our global budget? What our global budget shows is, starting back with the onset of the Industrial Revolution, is black is how much we've used up. The red is how much we have left if we want to stay below 1.5 degrees C. That budget that red is shrinking because this was data through 2017, which was presented in 2018 at the COP in Katowice. On the right-hand side, if we want to stay below 2.0 degrees C, it shows that we have a little bit more room. But basically what we're seeing is we can no longer use our atmosphere as a waste dump for carbon dioxide. Next. You'll see this 12 years left. This was a cry from youth in Katowice at COP25. They were standing there, 12 years left. That's what the reports say. We have 12 years left. If we don't peak by 2030, we will be exhausting our CO2 budget. And we cannot hold the temperature increase below 1.5 degrees C, and most likely not below 2 degrees C. Next. I'm going to jump forward to the most recent COP, which is one we just returned from in November, COP26 in Glasgow, Scotland. U.S. Special Envoy John Kerry called it our last best hope to get our act together. That was mirrored by UN Secretary Antonio Guterres. You know, it's our last best hope to get our act together. I will say once again, we went to Glasgow with the hopes. We thought, finally we get it. Everybody gets it. There was a 2-year lull because of the pandemic. They had been deferred, and we're going to get our act together. Next slide. So what did we get? We got the Glasgow Climate Pact. UN Secretary General Antonio Guterres summarized it quite well. He said the final texts take important steps, but unfortunately the collective political will was not enough to overcome some deep contradictions. Among those deep contradictions was the NDCs. We see a picture here on the left. In fact, my colleague who's here in the front row, Greg Foy, and I were sitting in on this session. It was the emissions gap report, which gave us the absolute latest data that everybody was dumping into COP26, so we know where we are. We fell all of those contributions, all those pledges fell a full 1 degree short of being able to hold down our planetary fever. On a positive note, for the very first time, this is COP26, we've been through 25 of them. For the very first time, fossil fuels and coal were inscribed into a text. Now, we got a copy of the draft of this text during the second week on a Wednesday, and we thought it was a done deal. Here's what it was to say, the draft was to say, parties are to accelerate the phasing out of coal and subsidies for fossil fuels. That's what the text said. Thought it was a done deal. By the end of the week, the negotiators wrangled fiercely through the night, but two nations, China and India, demanded that the language be diluted down to read, to phase down unabated coal power and to inefficient fossil fuel subsidies. So if you do it efficiently, you can subsidize them. You know, so and it is my understanding that the COP president and negotiators, many of them were literally in tears, because they had a done deal. At least they're inscribed in the text. Next one. I want to put this in response to what happened in COP26, and this goes up through 2018, which is the latest data we can get from the World Resources Institute, but it just plots, it's a plot of emissions for the 5 leading greenhouse gas producers. If you look at the top, you can see the United States in blue. We were the leading greenhouse gas producer until 2005. That's when China overtook us. You can see what their emissions scenario looks like. You can see what India's emission scenario looks like. So you have China and India. You can draw your conclusions from that. Okay? Next. I'm going to go back to Costa Rica now. Costa Rica has been a very forward-thinking nation. They have been for decades. They have been forward-thinking much of what they've done at the COPs, and in the most recent one, they initiated something known as the Beyond Oil and Gas Alliance. I might note it was a little hard to get into the press conference where this was released. A lot of people wanted to get in. It's the Beyond Oil and Gas Alliance. Basically, what they're saying, and rightfully so, is that in the past, to address our climate fever, we have put pressures on the consumers to control the emissions of CO2. However, the solution means that the only way to control it is if we phase out fossil fuels. They acknowledge it's not easy, it's expensive, it requires a huge amount of investment, but it is just, and it will create jobs. Okay. There is hope, but the hope requires a new way of thinking. We can't think as we have in the past. Next. For this, I'm going to jump back to Costa Rica once again, and we're going to go back to, I told you I was going to go to the Kabalanka Nature Reserve right there. We're going to talk about ecosystem services. Next. In 1950, 3/4 of Costa Rica was cloaked in lush forest. The government, however, encouraged individuals to clear the land. If you would clear the land and, quote, develop it, you could gain ownership of the land. If you look at that background slide, this is supposed to roll in, but anyway, if you look at it, you can see where we have a lot of pasture land that has been cleared and so forth. Through the 1970s, 1980s, Costa Rica the rate of deforestation in Costa Rica was the highest in North America. By 1987, it had lost a full 30 to 50% of its forest cover. It was very clear that resource consumption was rapidly outpacing preservation efforts. Next one. Now we're going to go back to Kabalanka Nature Reserve. In the 1960s, early 1960s, a young Swede by the name of Nicholas Vestberg had just arrived with his wife, and he went to the southern tip of the Nicoya Peninsula in Costa Rica. He saw where all this land had been denuded, these beautiful trees toppled down, being used for pasture land. Shocked him because he had come, expecting something quite different. He put forth a lot of effort. It wasn't easy, but he was able to cobble together international support, even got some resistance, but finally the government to agree. They created the first protected reserve in all of Costa Rica, but it also was the first protected land in all of Central America. Now, there were others involved at the same time. We had the Monteverde cloud forest and so forth, but the preservation efforts were going against the deforestation. This is a picture of the Kabalanka today. I've tramped through it many times, and it's a developing secondary forest with fauna coming back in, and they're just letting it happen as it will. Next. In 1996, Costa Rica passed a law where they made it illegal for anyone to log any forest without the approval of authorities. They introduced something known as payments for ecosystem services. This was 25 years ago they introduced payment for ecosystem services. They also, and what it does, it rewards farmers who implement practices of sustainable forestry and environmental protection. In 2020 or 2012, they passed a ban on sport hunting, and in 2020 they received one of the UN's highest award for climate action. Next. So what are ecosystem services? Basically, it says that humans draw a direct benefit from healthy ecosystems and from the beauty of the natural environment. These ecosystems include things like forest ecosystems, aquatic ecosystems, grasslands, the cryosphere ecosystems, and more. Next. Today, forests cover nearly 60% of the country. If you look there, people go, as I just did coming 2 weeks ago, and some of the others in this audience here, you went to Costa Rica not to cut down the trees, to sell them for lumber here, or to mine for gold, or look at their other resources and take the resources, but rather you went to get a picture of a resplendent quetzal, or as I did, looking at a sloth as I'm eating lunch, and you see it not 20 feet away from me, or even a red-eyed tree frog. Next. This brings us to the point, the issue of natural capital, which was actually coined in the 1970s, and it's a very, very important and growing issue, statement in economics. Natural capital states that nature is priceless, but it is not valueless. There's significant monetary value in nature just being nature, cleaning the water, preventing erosion, cleaning the air, and more. Next. Brings us to the way we measure economic activity. We use something called gross domestic product. We all know it, GDP. You hear it all the time, GDP. GDP is a snapshot of our economic activity. However, it places monetary value only on goods and services. It does not take into account non-market transactions, which include environmental degradation, the well-being of society, and whether or not this economic growth is in fact even sustainable. The emphasis of GDP is on destruction, not on preservation. Next. In March 2021, go back to that last slide. I want to point something out. This is what's sometimes called the Mickey Mouse model of sustainability. The head is economics. It's all about money, and we know that. Sometimes lending an ear maybe to sustainability, maybe to society, but it's all about money. Next. To be truly sustainable, the social, the environmental, and the economic components have to be in a balance. It's many times called the 3 Ps: people, profit, and planet. Next. The UN in 2021, just last year, UN Statistical Commission adopted what is known as the UN system of environmental economic accounting, which is to replace GDP. This is a new, looking at the bold, the new ecosystem accounting framework, SEEA or -EA, is a transformative view that puts value on nature itself. Basically, the intent is to ensure that the treasury of the commons we all enjoy does not degrade into the tragedy of the commons of what we are actually seeing under our current economic models. Next. Currently, more than 90 countries have adopted SEEA accounting, and they are, expanding on it. The U.S. has not yet done so, but it's considering it. Next. And this brings us up to the last slide, and I put this in based upon the report that was just released on Monday. And basically what that report says, the evidence is clear, the time for action is now. They're pointing to 2025, 2030 at the latest. We can no longer kick the can down the road. The time for action is now. Without immediate, and this is a quote, without immediate and deep emissions reductions across all sectors, limiting global warming to 1.5 degrees will be beyond reach. So, with that, I'll conclude by saying thank you. Thanks for listening. I hope that I've given you some information, the background science, and some connections. It's a massive, massive issue, but I think it's one that we can't just ignore and just say it's just too complex. We can, and we can do something about it. So I'll answer questions or even invite comments from anybody who wants to share your voice.
I'm of the opinion that population growth is one of the biggest factors. The next 30 years, it's projected that we'll grow another 1 billion people. I look at this crowd here and I say, hooray. But I also say, why isn't the room filled? We're just not there yet. I don't know how to spread the word. What do you know about what is being done about population? The Chinese take a lot of shots and well-deserved, but their one-child policy was not a bad one. Thank you.
I think I probably will forego that question only because I think that's one that requires a tremendous amount of dialogue, and it's a very, very deep, it's a deep issue. Obviously, humans are having an impact on the planet. We see it.
What we can say, even without getting into that, is we as humans have to recognize that in the Anthropocene, we do have a responsibility as a species. And I've listened to some seminars, and my fiance was here, we listened to one that was just deeply compelling, that says the responsibility now falls upon us as a species.
Can we make a comeback when we go over 1.5?
I wish we could. If we don't peak and we go to 1.5, the ship is not going to turn around immediately. It's a little bit like heading the Titanic heading for the Glacier, and you say, okay, we're starting to scrape it, let's turn. And the answer is, if we use up our carbon budget, it would take centuries to sequester the CO2 at a rate to turn it back to 1.5 degrees. So I guess the answer to that is no. I'm looking at my colleague. You agree with that? All right.
There seem to be some wonderful technologies that seem to be emerging, although on small scale, and maybe not at the speed of introduction and innovation in terms of carbon sequestration. What are your thoughts on carbon sequestration technologies?
I'd invite my colleague here to give some responses as well if you want to step up to the mic. But I mean, carbon sequestration, there are possibilities. I don't think it's going to solve our problems. I think it's going to be a contributor, and that's being proposed in the most recent report as one of the efforts is to try to sequester carbon. Quite frankly, one of the best ways to sequester it is just to have nature, photosynthesis, take it out, as well as using technologies to do it. And of course, I didn't put in here like the transformations are required, but we absolutely must go to electrification. We must get away from using this stored solar energy, which is all that fossil fuel is. Fossil fuels are, they're just stored solar energy, and they're currently cheap because we don't take into account the economic issues. We have to revisit our cities, and some cities are doing that. Revisit our cities and look at how we move people, how we walk, and how we physically move people. We need to start to look at things like hydrogen technologies, fuel cells, the emissions, or water. If we use solar energy to generate the electricity, to convert the water into hydrogen and oxygen gas, we have the fuel to do it. So we need transformative way of thinking. We can't think in the way we have in the past. That sort of went beyond what your question was, but I hope I sort of touched on it. Okay?
There's a question on the board about what percentage of the U.S. has been deforested? Are there any statistics on that?
Yeah, when you say deforested from, you pick a certain time, what is do you know a number? I wouldn't know the number. Yeah. Yeah. And deforestation and agricultural use, and that's a major contributor to CO2 emissions and greenhouse gas emissions in general, other greenhouse gases.
No other questions. We want to thank you so much for being with us.
Okay, thank you.